Non-traditional machining, part 2. So welcome to the second part of this lecture series on non-traditional machining, and to begin with, we'll be starting with conventional machining so that we can later on distinguish between conventional and non-conventional machining. And in this part, we are going to discuss about two very important conventional machining processes, which are turning and milling. I am Dr. Gurraj Singh, and this lecture is going to be split into 6 different parts. To begin with, we'll discuss the introduction to the turning process. Then we'll throw some light on the machine that is used for turning, that is lathe, its different parts and its types. Then we'll talk about the cutting tools that are used in the turning process. And then likewise, we'll be discussing the same steps for the milling process: the introduction, the milling machine parts and types, and the cutting tools used. So turning is basically a process where you are trying to reduce the diameter of a cylindrical workpiece that is held on a rotating chuck, which is a device that is used for holding this workpiece, and the machine that is used is your lathe machine. So turning is a form of machining process where the material removal takes place from rotational parts and we cut away all the unwanted material. The process, it requires a setup, and that setup includes a turning machine, which is a lathe, a workpiece, a fixture which is used for holding the workpiece, and a cutting tool like these ones, 1, 2 and 3. So we need these 4 things for the turning process to take place, and the workpiece is basically secured in a fixture, as we saw in the previous slide, that the workpiece on a rotating fixture is allowed to rotate at very high speeds, and the cutter, which is typically a single point cutting tool, so this is important here. The cutter is a single point cutting tool and it is secured in the machine, although some operations may use multi-point cutting tools as well. And then there are certain parameters that need to be varied in order to perform the process, like giving away feed, then giving a depth into the workpiece, a depth of cut that is usually called as, and eventually we end up changing the shape of the raw material into a final product. So turning process, to know more about it, it is used to produce rotational and axisymmetric products which have many features such as holes, grooves, threads, tapers, and various diameter steps. So it can produce all these different features on a workpiece, and it can also produce contoured surfaces. So it is possible to give all these features using the turning process, and the parts that are fabricated completely through turning often includes the components that are used in limited quantities or perhaps for prototypes. It is commonly used as a secondary process to add or refine the features. So normally we refer to processes as primary or secondary. Now you're using turning process after the primary operations of converting maybe a cubical block into a cylindrical workpiece has been done, probably by casting or by forging. And now in order to give it the final shape or to give it certain features as mentioned above here, the turning process is used. So it is mostly a secondary manufacturing process. And due to the high tolerances and surface finishes that turning can offer, it is ideal for adding precision rotational features to a part whose basic shape has already been formed. So this tells us that turning is a very important process where you need to shape axisymmetric or cylindrical components, and it is mostly used as a secondary process. Now what are the various turning parameters? All these are the parameters used in turning: cutting speed, cutting feed, spindle speed, axial depth of cut, and the radial depth of cut. So now the most important ones here are the radial depth of cut, the cutting feed, as well as the cutting speed. Now there is a relationship between cutting speed and spindle speed. Usually the cutting speed is expressed in meters per minute and the spindle speed is expressed in revolutions per minute, RPM. So basically, the spindle speed, it refers to the speed at which this workpiece is being rotated, or the spindle is rotating, or the chuck is rotating. So how many revolutions per minute is it rotating? And whereas cutting speed is the speed of the workpiece surface with reference to this cutting tool. So what distance is this surface moving with reference to this stationary tool, and it is expressed in meters per minute. Now when I talk about cutting feet is the distance, or it is the distance per revolution that the tool is moving in this direction. So you need to reduce the diameter. You're going to move the tool from here and you're going to start moving it to the left, so as you keep on reducing the diameter till the end, or till whichever point you want to reduce it. So this distance that it covers per revolution is known as feet, and feet is usually a very small number, for example 0.01 mm per revolution. So 1/100th of a millimeter per revolution of this workpiece is what the tool can move in this direction. And then depth of cut is basically this depth, how deep you want to go, how much diameter do you want to reduce. That is called as the depth of cut. So speed, feed and depth of cut, these are the three basic parameters that are used in the turning process. Now we come to the lathe machine. So when we are performing turning, we need to use this setup, this machine tool, and it's called as a lathe. Now a lathe, it has many parts, and those parts, each of that part has its own typical function. Now this particular part, this portion of a lathe machine is called as the headstock, and this portion is called as the tailstock. So obviously this is the head of the machine and that's the tail of the machine, the front end and the rear end. So the headstock, it contains various controls, and it contains the powerhouse of the lathe machine, which basically rotates the workpiece which is held on this chuck. So this is having different gearbox controls, it is controlling the feed box, it has the basic engines or the motors, whichever are the power source of this machine. So that's comprised by the headstock. Then you have the chuck. Now I've written a 4-jaw chuck here. It can be a 3-jaw chuck as well. There are different types of fixtures that may be used for holding the workpiece. Then on the tailstock side, you have the tailstock assembly, where you can have a dead center and a ram, and that is normally used for supporting a very, very long workpiece in order to turn it properly. Then you have this bed of the lathe machine, which is the base, and then you have a tray on top of that bed. Then you have a carriage here. So this carriage is the very, very important component of the lathe machine, and this carriage, it contains the movement of the tool. So first of all, you'll have a carriage on top of which you'll have a cross slide, and then you have a tool post. So this tool post, this is where your tool is going to be held. This is where the tool is going to be held, and these controls are going to control the movement of the tool. So you can move the tool in X, Y or Z axis. All that is going to be controlled by these components. Alright. So here the parts have been mentioned. So you have a bed, you have a headstock assembly, then you have a tailstock assembly, you have a carriage, a cross slide. On top of the cross slide you have a compound rest, and then the tool holder is also referred to as the turret. So these are the important components of a lathe machine. Now let us see how many types of lathe machines are usually there. So normally we have these 6 types of lathe machines that are used. Now the most common ones that we use can be the tool room lathe that the students normally get to see in the university workshops, or the engine lathe, which normally has an engine But these days we are not using engine lathe, instead we are using the motor run electric lathes. Then you have a high speed lathe machine. So this lathe machine, it specializes in high speed rotation. The RPM at which it can rotate the workpiece is much higher as compared to its counterparts. Then you have a bench lathe machine. So this is normally a very small sized lathe machine and much smaller as compared to maybe a tool room lathe or an engine lathe. And this is used for smaller components. So as it says, bench lathe machine, it can be fit on the top of a table or a bench. Then you have a turret lathe machine. So a turret lathe machine now, its functionality is entirely same as all the remaining lathe machines that are there. But the only difference is in terms of the tailstock assembly. Now, it does not have a tailstock. Instead, it has a turret fixed at its tail part. And this turret can hold multiple tools. And this machine is generally used for mass production, where you need to change the tool regularly after fixed intervals. And this can normally be used for those areas where you need to produce large number of parts and you need to have very low cycle times. And then lastly, you have the CNC modern cutting tool rooms, which use these CNC lathe machines. So these are program run lathe machines. These are computer numeric controlled lathe machines. You can feed a program on this controller here, and once the program has been fed and once you are running the program, the parameters, namely speed, feed and depth of cut, can be varied in terms of the program that has been fed into the lathe machine. So this eliminates the human intervention, or the scope of human error is eliminated using a CNC lathe machine. Now, what are the specifications that you need to know whenever you're discussing lathe machines? Well, you need to take a look at the length of the bed, the distance between the centers, it is this distance, then the swing diameter of the work over the bed. So this generally is the swing diameter, this one. Then the swing diameter of the work over the carriage, which is this particular length. And then finally the power input. What is the power input in case it's an electric lathe? Then the lead screw details. Now we all know that lead screw is a very important component of the lathe on which the carriage moves. Then the number of spindles that we have, the different feed combinations that we can provide, and the width of the bed, the base. So these are the specifications that you need to take into account whenever you're planning to maybe procure a lathe machine for your workshop. Now, what are the processes that can be performed on a lathe? So you have all different forms of processes that can be used. If you want to shorten the length of a workpiece at the end, you want to just flatten this end. For example, sometimes we have a cylindrical component which has an uneven end. You want to just flatten this, finish it. You will use the facing operation. You can also use taper turning to give a taper to the shape of the component. Then contour turning, the shape of a curvature can be provided, which is also called as a contour. Then form turning, so you can use a tool that can give a certain form to the workpiece. Chamfering, now in order to remove the sharp edges, you can chamfer the end of the workpiece and blunt it basically, and that is called as chamfering. Then cut off or parting off. So parting off is another process where you want to cut this component into two parts, 1 and 2. That's called as cut off. Threading, where you want to put threads on the workpiece. Then there are related processes which are boring and drilling. Now you want to drill a hole at the end of the workpiece, you can put a drill tool on your tailstock. And similarly, you want to increase the size of an already drilled hole. You call it as the boring process, and this is also called as internal turning. So internal turning or boring is used to increase the size of an already drilled hole, while drilling is the process which is used for creating a new hole. And knurling, lastly, is a process where you use a knurl tool, and that is used for just imprinting a pattern on the surface of the workpiece to give it an aesthetic look, or maybe to give it a gripping effect. So these are the different processes that can be performed on a lathe machine. Now we come to the cutting tool that is used on a lathe machine. The cutting tool that's used on a lathe is usually referred to as a single point cutting tool. It has one cutting point, and that's why it's called as a single point cutting tool. This is how the tool looks like. And this is the normal geometry of a tool. So you have this component which is used for holding purposes is called as the shank. And this is the point where the actual cutting takes place. And this is called as the nose of the tool. This radius of this portion is called as the nose radius. So if you take a look at this from the top, it has a certain radius here. And this is called as the nose radius. Then you have a back rake and a side rake angle. Now these angles which you can see here, these angles are basically given at the top of the cutting tool surface to direct the chips. Because whenever you're performing a cutting operation, you're going to produce chips which are the waste products of the cutting process. And those chips, the material that is removed, they need to be directed properly in order to prevent them from interfering in the turning process. So therefore the rake angles, they make sure that the chips do not interfere in the future cutting. Then you have the end relief or the side relief angle. Now what is the relief angle? So these relief angles, this one and this one, they are basically to prevent the tool from coming into contact with the workpiece at any other point. So the end relief and the side relief, these two angles are to prevent interference. And then you have the end cutting edge angle and the side cutting edge angle. So these are basically the angles that your end cutting edge and the side cutting edge are making with the perpendicular. So this is the geometry of a single point cutting tool. And this is a modern single point cutting tool, and this is normally used for machining harder materials, because you cannot machine, say, titanium using a softer tool. And in case you want to machine titanium with a harder tool, you need to use a material that is harder than titanium. For example, you want to use tungsten carbide in this case. So a coated tungsten carbide insert has been used here. And now why not make this entire tool out of tungsten carbide? Because that is going to increase the cost. So in order to prevent the cost from increasing beyond viability levels, you are trying to make just the cutting part out of the expensive material, while the remaining tool that is just used for holding that cutting edge, so you can make it out of a cheaper material like mild steel or high-speed steel. And this can hold this harder material. You can just grip it here using an Allen key setup, and this can perform the machining operation for harder materials. So that's how the modern turning process has evolved. And these are the different types of turning tools that are used in different cutting operations. For example, you want to give external threads, you want to give internal threads, chamfering, then you want to give a groove, you want undercutting tool, you want to face, ream, or you want to bore. So you have dedicated cutting tools, dedicated cutting tool inserts rather I'd say, for different cutting operations. And that's how the insert is usually held, using a clamp and a screw. You just put the insert on the insert seat, and then you can simply tighten this screw and the clamp setup, and you can hold the insert in the right place. And you can perform the cutting operation. Once this insert wears out, you can remove this insert and you can change the insert, while this tool holder, it remains the same. So this is again a very, very nice depiction of different processes which can be used on the lathe. So you can see this is the cutting off tool. This is used to cut a workpiece into two parts. This is used for back turning. Now, if you want to turn in this direction, it's called as front turning. If you want to turn in this direction, it's called as back turning. So this is a back turning tool. Likewise, this is a grooving tool, and this is used to perform or to make these grooves. So you can see these patterns there. These are the grooves. Again, the front turning tool, and this is the most commonly used tool in the lathe machine. This is the most commonly used tool that we normally use. Then the threading tool, so this is used for making threads. And then finally, this is the boring tool. So you see, this is the cutting edge, and you hold it onto the tool holder like this, and this cutting edge can be used for performing internal turning. So this is how the cutting tool technology has evolved over the past couple of decades, and this is how the turning process has turned out to be highly efficient in machining even harder materials. Next, we come to milling process. Now, what do you mean by milling? Milling is a similar process when you compare it to turning, but there's actually a huge difference. In case of turning, it is your tool that is stationary while your workpiece that is rotating. But in this case, you can see that it is this tool that is rotating while the workpiece here at the base is stationary. So it is this tool, or it is this tool that is held on the spindle, and this is the revolving or the rotating part, while the workpiece is just stationary. So this is the basic difference between a turning and a milling process. So milling is the most common form of machining that creates a variety of features by cutting away the unwanted material. And as in turning, the milling process also requires a milling machine, a workpiece, a fixture, and a cutter. And the workpiece is a piece of pre-shaped material that is secured to the fixture and is itself attached to a platform inside the milling machine. And the cutter is a cutting tool with sharp teeth. Now, one more thing, unlike in case of the turning process, this milling cutter is not a single point cutter. It is a multi-point cutting tool. It has multiple points here. You can see it has multiple cutting edges, unlike in case of your lathe machine, which is a single point cutting tool. So this is yet another difference between turning and milling. And by feeding the workpiece into the rotating cutter, the material is cut away from the workpiece in the form of small chips which are used to create the desired shape. So this is a basic introduction to milling. And now, what are the applications of milling? So milling can be used to produce parts which are usually not actually symmetric and have many features such as holes, slots, pockets, and even 3D surface contours. So you can see these parts. These have been manufactured by a milling process. So you can give all these different shapes, these contours, these cuts using a milling cutter. And the parts that are fabricated completely through milling, they often include components that are used in limited quantities, perhaps for prototypes. So even milling process, it can be used for manufacturing prototypes that can later be probably, it can be used for making patterns in casting. So a pattern is normally a prototype. And to make that pattern, maybe out of metal or wood, you can use a milling process because it can give all sorts of these features to the workpiece. Another application of milling is the fabrication of tooling for other processes. So you use a milling process for making tools for the other operations. So milling cutter is normally used for making cutting tools that are used in other cutting processes. And again, it is commonly used as a secondary process. So the turning process was also secondary. The milling process is also a secondary process that is used to add or refine the features. And due to the high tolerances and surface finishes, it is an ideal operation for adding precision features. So these features, they are all precision features and they've been added using a milling process. So milling machine. Now this is how a milling machine looks like. And just like a lathe, a milling machine has its own individual parts. So if I come to the work holding part, you have a base at the bottom, and on the base you have a knee, and that knee holds a saddle on top of it. And it is this saddle which contains the vise that is used for holding the workpiece. And now when I come to the tooling part, it is this ram that is having the power source for this milling machine, and it is holding the tool on the spindle head, and the milling head, it contains usually the motor that is used to drive this spindle and then give the rotation force to the milling cutter. And these milling machines are usually of two broad types, a horizontal milling machine and a vertical milling machine. Now you can see the difference here. In case of your horizontal milling machine, the arbor which is holding the cutting tool here, its axis is horizontal when you compare it to the surface of the saddle or the workpiece. These are parallel to one another. But in this case, the surface of the workpiece or the saddle, it is perpendicular to the axis in which the milling cutter is held. So that's the basic difference between a horizontal and a vertical milling machine. Now your milling machines are usually of four common types. I'd rather say three, because a rotary milling machine is also not very commonly used, but a vertical, a horizontal and a universal milling machine. So we have seen both vertical and horizontal machines, and as the name says, a universal milling machine, it can be used both as a horizontal or a vertical machine. So you will have an adjustment here, and you can either use the tool in a parallel axis or in a perpendicular axis. So that's a universal milling machine. Now there are certain types of cutting procedures in a milling process which you need to know. So the two most important classifications here are either up or down milling or peripheral and end milling. So these are the two broad categorizations that you need to know: up and down, peripheral and end milling. Now first of all, let's talk about up and down milling. Now you can easily see here that in case of up milling, your workpiece feed is in the opposite direction to the direction of cutting of the cutting tool. So you see the cutting tool is rotating like this. So the workpiece is moving in the opposite direction. So you can see your tool is moving uphill. So you call it as up milling. But in this case, you see that the workpiece feed is in the same direction to the direction of rotation of the cutting tool. So this is called as your down milling process, where these two directions are similar to one another. Now let us see what are the basic differences between up milling and down milling. So the cutter rotates against the direction of the table in case of up milling. The cutter rotates along the direction of the table in case of down milling. The chip load on the teeth increases gradually from 0 to maximum during the contact period of each tooth. So in case of up milling, you can see that the chip that is being produced, its shape is like this. So its thickness is gradually increasing as the cutter is moving upwards. But on the other hand, in case of your down milling, the chip thickness, it is maximum when the cutting starts and it is minimum when the cutting ends here. That's because of the relative motion between the workpiece and the cutting tool. So the chip load on the teeth gradually decreases from maximum to 0. So therefore, in this case, the chip load initially is minimum, and by the time it reaches here, it is maximum. Therefore, I've told that it is from 0 to maximum. But in this case, it is maximum here, and by the time the cutting ends, it is 0. So therefore, I've mentioned maximum to 0. Then, the cutting force in up milling is directed upwards. So in case of up milling, your cutting force is going to be in this direction, while in case of your down milling, your cutting force is going to be directed downwards. The burr is formed only on unfinished surface ahead of the tool feed, However, majority of such burr is removed in the subsequent passes. So the burr formation takes place here. But as the tool moves ahead, it's going to be replaced, it's going to be cut. So it is removed easily. But unlikely in this case, the burr is formed at the finished surface in the opposite side of the tool feed, and thus the burrs are not removed automatically. And this leads to degraded cutting quality. That burr is formed here, and this tool is moving here. So this burr will remain, and you'll have to remove it later on using separate cutting operations. So next, the tooth experience gradual loading as contact starts with zero chip load. So you see that in this case of up milling, your tooth, now this is the tooth, so these are the different teeth of the milling cutter. So they will experience gradual loading because initially the load is zero. So it increases slowly, so it does not exert a lot of force on these teeth. But in this case, you see maximum at the start. So therefore, it is going to experience impact loading due to sudden mating with the maximum chip load. So in the starting only, it is mating with the maximum chip load, and therefore it is going to face impact loading. No backlash eliminator is required for up milling, while a backlash eliminator is required for down milling. And this is normally in case when you have play in case of an old machine. So you will require to remove backlash. Next, we need to differentiate between end milling and peripheral milling. Now you can easily see that in case of end milling, which is this process, it is this end portion of your cutting tool that is doing the cutting. But in case of a peripheral milling, it is the entire periphery of the cutting tool that is performing the cutting operation. So end mills are the tools that cut wood and metal in the milling process, and they have cutting teeth on the face and edge of the body. And unlike a drill press, which typically bores vertically, they cut into materials with a circular motion from side to side. So basically, this end milling cutter, it cuts the workpiece with a specific depth of cut, and it does not cut the workpiece very deep. It can only cut on the surface to give a certain depth, but it is this portion that does the cutting. So these portions are not involved in the cutting process. However, in case of peripheral milling, it is where the cutter is placed parallel to the workpiece. So again, this cutter, its axis is parallel to the workpiece surface. However, in case of your end milling, the axis of the cutter is perpendicular to the workpiece axis. So that's again a very significant difference between end milling and peripheral milling. Now, after learning about end and peripheral milling, there's a third term that is called as face milling. Now, what is face milling? Face milling is similar to end milling. That means that the cutting tool rotational axis is perpendicular to the surface of the workpiece. So it is perpendicular, like you can see here. But the difference in case of face milling and end milling is that it can be very easily seen in these two images. The image at the top, it shows face milling, while this image at the bottom, it shows end milling. Now in both these cases, the cutter axis is perpendicular to the workpiece. However, the width of the cutter is very, very large in case of face milling, and it is very, very small in case of end milling. So the relative width or the relative size of the cutter and the workpiece is very large in case of end milling process, while it is nearly similar in case of face milling process. So the most significant difference between end mills and face mills is in their designs. And end mills, they use both the ends and sides of the cutter, while face mills, they complete horizontal cutting using a circular and sharp edges along with their circumference. So these are the cutting edges of a face milling cutter. So these are the different types of milling cutters now that are used. So you can see that this is a normal end milling cutter, and this is a face milling cutter. So you can see the size difference. An end milling cutter is very much comparable to a drilling tool. The only difference being that it is not pointed at the bottom and does not have two cutting edges, but rather multiple cutting edges. And a face milling cutter is relatively larger, and it has these inserts which are connected at the end, and it is this point which is going to perform the actual cutting. And apart from that, we have these concave milling cutters, the side milling cutters, you have the fly cutter. Then in order to give a rounded cavity, you have a ball cutter, a wood rough cutter is there, and thread mill cutters are also there. So you have different types of milling cutters which are used to perform different milling operations. Now what are those different milling operations? So this will make things pretty much clear now. So you can see now this is a normal end milling process. 1, 2 and 3. However, this is more of a face milling setup. And using a milling cutter, you can make a square shape. You can make a T-slot here by using this type of a cutter. You can make a ball. So a hemispherical cavity you can create using a ball cutter. And you can create a shell. So different types of cutters can provide or can be used for making different shapes. Again, if you want to compare end milling and face milling, you can easily distinguish between the processes using these images. Now you see, this is pure face milling and this is partial face milling. So you can see the comparison between the cutter size and the workpiece width. They're pretty much similarly here. But this is end milling, where the cutter size is very small while the workpiece is very large. So that's how you perform end milling. And this end milling process can be used for making pockets as well. So you want to create a pocket in the middle, or you want to give a surface contour, you can use the end milling cutter. So this is all about turning and milling. In the next lecture, we'll discuss drilling and grinding. Thank you.